I'll take a few minutes talking about TLB, which I introduced last time, and try to give an illustrative example, and then we'll move on to the next topic, which is input-output. Okay, so when we discuss virtual memory, uh, keeping in mind the large space requirement for page table, we talked about uh, keeping the page table in virtual space. Okay, so that actually brings us to this point that for every access to the memory, you would require 3 physical accesses, okay, which is quite bad, and therefore we talked about introducing a translation look-aside buffer, or TLB. So TLB is like a cache for PT. Okay, if a page table were the main memory, then TLB is like the cache. Okay, what is meant by this is that the last few accesses made to page table would get recorded in the TLB, and any repeated access to that can benefit from availability of that information within the TLB. So here I'm showing TLB as a lookup table or an associative structure where you look through it, look up by supplying the virtual page number, and what you get is the physical page number. Okay, so there is a valid bit which marks which entries are valid, which are not valid, and in a fully associative TLB, you would expect that the VPN which you are supplying is matched against all the first field entries of this, and the second field gives you the physical page number. So you need to keep in mind that the whole structure now involves 3 things: TLB, cache, and page table. So normally you start with first making access to TLB, because before you go to cache, you need to have the physical address. So TLB is supposed to help you in that. If there is a TLB hit, that means the VPN part of the address matched some entry in the TLB and valid bit was 1, then it's a hit and you can make cache access. If not, then you need to look up the page table. Okay, page table also may tell you where the page is which you're looking for, or if it is not there in the main memory, you will get a page fault. Okay, so if page table access is successful, you get the physical page number, and whether you get physical page number from TLB or page table, you have the physical address and you are able to access cache. So at cache level, they may be again a hit or a miss. So the 2 possibilities are there. If there is a hit, then your job is done and you can deliver the data to CPU if you're reading, or you can perform a write. If there is a cache miss, then you need to go to the next level. Okay, suppose the next level is physical memory, so you make access to physical memory, get a block in the cache, and read the word you wanted. If there is a miss at the page table access level, then it's a page fault, and page need to be obtained from the backup storage or disk. Also, what is not shown in this diagram is that page table access also means a complicated process. For example, if it is if page table in virtual memory, then you need to make an access through the translation of page table addresses which are in system virtual space to physical space. Okay, and any main memory access also has to go through cache. So even if the page table was in physical memory, you don't access that physical memory directly because some part of the page table may be in the cache. Okay, so this page table access is not just one single uh, operation. It may involve a sequence of operations. So we also talked about virtually addressed cache, where you can uh, directly access cache from the virtual addresses. Okay, that means that the tags which are stored in the cache come from virtual addresses, not physical addresses. So what is the advantage of that? That if your cache is physically addressed, then one step is TLB access and one step is cache access. Typically, you will require at least 2 cycles. In a virtually addressed cache, you can do it in a single cycle. So if you're lucky, you supply virtual address, you get cache access, and if there is a hit, you are done in a single cycle itself. Uh, but as I mentioned, there are some problems like that of aliasing, which will not go into detail. So therefore, what serves the same purpose without the problem of aliasing and such things is a physically tagged and virtually indexed cache. Okay. However, that scheme is possible only for caches which are small enough. So imagine that cache is of size. Imagine a direct mapped cache which is of size of a page. Okay. So then the offset uh, of the word or byte within the page is good enough to get you index into cache. And while you index the cache, uh, virtual to physical translation could happen in TLB, and if that is successful, you can uh, do the tag comparison after that. Okay, so uh, this is a simple arrangement, but possible only in limited sense. Okay, now let's take a small toy example and see how actually you work with TLB and page table uh, for a given sequence of memory accesses. So this is derived from an example from the textbook. This number may be different in different editions, but I think you'll be able to spot it. So suppose we have a page table containing 12 entries. Okay, that means the virtual memory has 12 pages. Okay, so it's a table with 12 entries, and as you can see, some of these are zeros, valid bits are 0, and some are 1. The entries which are 1 correspond to those virtual pages which are there in physical memory. Okay, for example, uh, virtual page number 0 is there in uh, 5th page of the physical memory. Okay, virtual page 3 is in the 6th one, and so on. Uh, on the other hand, we have a TLB, which typically would be much smaller than the page table size. So it's a TLB is a special piece of hardware within the processor. Okay, it's a dedicated structure which is not very large. You know, there may be few hundreds or at most few thousand entries in this. So there is a valid bit, there is a tag part and the VPN part. So tag is same as the VPN. If you come with a particular VPN value, you can look up here. If there is a match and VBit is set, then you get the VPN part of it. So assuming that it's fully associative. Okay, suppose the page size is 4 kilobytes and we have a sequence of virtual addresses which are being which are being supplied by a program. So that means the program is making access to virtual address 4095, then this 31,000 something and so on. So there is a sequence of addresses which are being referred to. Okay. And given this state of PT and TLB, we'll try to figure out where the miss will occur, where hit will occur, and what action will take place. So from these virtual addresses, what we need to figure out is the virtual page numbers. Okay. So page size being 4 KB, that means 4096. Okay. You can take you can divide the virtual address by the page size and look at the quotient. So 0 for this, 7, 3, 3, 1, 1, 2. So this is a sequence of virtual page numbers that are being accessed. Okay. So starting with 0, we'll first make an access in TLB. And as you can see that there is no entry for 0, therefore it will be a TLB miss. So I am going to record it here, TLB hit or miss. So I'm saying with first access there is a miss. When TLB miss occurs, we go to the page table and check if there is a valid entry. So for page 0 there is a valid entry, and that's page number, physical page number 5. So there is no page fault. We had a TLB miss, but no page fault. What we do is, of course, page can be accessed, but we update TLB. We create an entry for 0, and what we have done is we have replaced an entry because TLB is of limited size, so something has to go out for something new which has to come in. And if there is a invalid entry, that's a good place to put it there. Otherwise, we will have to replace something which is valid. So we put this entry 05 here and mark it as valid. Okay. Next page number, next virtual page number is 7, and we have a hit here. Okay. So we don't need to go to page table. I record it as a hit. And next two accesses are to page number 3, which is also a hit. So that's straightforward. After that, we are accessing virtual page 1, which is again a TLB miss. And we go to page table. Again, there is a miss. So it's a page fault. All right. We'll get information here about location of that page on the disk. We do that and place it in some physical page. Okay, let's say we chose to put it in page 13 of the physical memory. So now in the PT, new entry has been created. It's a valid entry. And what it says is that for page virtual page 1, physical page number 13 has been associated. Yes, is there a question?
How did you associate, like why did you associate page number 13 to, sorry, to this page
Yeah.
21?
Yeah, so good question. Why did we choose 13? That is not showing up here in this example. But what comes into play here is the replacement policy. Okay. So I would have looked at, suppose I am following LRU, least recently used policies. So I would keep track of which page is being accessed when, and the one which was accessed farthest back in past is the least recently used page, and I'll replace that. So suppose result of that exercise told me that it is page number 13 which has to be replaced, and I have replaced 13.
And sir, why is there a need to replace, it puts 13 there? Like why couldn't we have just disk? It's all
Okay.
that we don't have a memory there.
No, no. Physical memory has limited size, so limited number of pages can exist. Uh,
No, my doubt is like why did we? It was a display. It was that no page was associated with one, right? Initially.
yeah, yeah.
Then why is it necessary to put 13 then? Why
Uh,
couldn't we just
okay.
proceed as it is?
All right. So actually, I think there is an anomaly in the numbers here. Imagine that the page table is not this much. There is much larger because this seems to give an impression that virtual pages are from 0 to 11 and physical pages are going as larger than that, 12, 13 and so on. So typically virtual space is larger than the physical space. Okay. And just to get that right, imagine that we are looking at only part of the physical part of the page table. The page table is going down further, and maybe physical page number 13 was occupied by some other virtual page. Okay, so either we find a physical page which is free, then we can allocate that. If we don't find any physical page free, then we need to pick up one which causes us least harm. Okay, and these replacement policies try to actually identify which page needs to be replaced. Okay, so let's say page number 13 was containing some virtual page which we used long time back, and we are not likely to use it again in near future. So we from physical page 13 we remove the old virtual page which was sitting there and put the virtual page number 1 there. That's what is happening.
So, sir, let's say 13 contains some garbage value initially. Like the page may have something where some values, right?
Yeah,
Stored. So, since the valid bit is 1 and we stored we mapped the 13 to page number 1, like
yeah,
page table entry 1. So,
yeah.
whenever next time the memory has like says I need to access 1, then it will supply the garbage value,
No,
right?
no,
The
no.
program will supply the garbage.
So you see, what we would have done is that we would have brought virtual page number 1 from disk and put it in physical page number 13. So 13 might have been containing garbage earlier, or 13 might be containing a different virtual page. Whatever it was is now replaced with uh, virtual page number 1.
Okay, so the data in the disk initially has been put into 13 kind of.
Yeah, yeah. So
Okay.
initially, you see, before the program is run, the virtual memory is all set up. Okay, which means that your code and data all have been assigned some virtual space and put somewhere in disk, right? Uh, then you set up the page table where the page table has to be located and so on. So just for the moment, assume that in physical memory somewhere you have allocated space for a page table.
Okay, okay.
Initially, you make everything as invalid. Its page table is allocated space, but all entries are invalid because we haven't put anything. Your code and data, everything is sitting in disk somewhere. So initially, you get a lot of page faults. You bring in pages as a result of that and start filling up physical memory with the virtual pages and keep making valid entries in the page table. So right now we started somewhere in between where uh, there were some valid entries in the page table. That means some virtual pages at this point of time are sitting in physical page locations. Okay, while some virtual pages are still on disk.
So I have a question. So, if we allocating page or the physical memory of page 13 with virtual page number 1, so can we have such a case so all the physical page number are full? Then what will we do?
Yeah, yeah. So of course that will happen quite often. Uh, there would be a time when all physical memory pages are occupied. Then if a new page has to be brought in, new virtual page has to be brought in, uh, some some old virtual page has to be displaced.
Okay, sir.
Yeah, because all virtual pages cannot uh, come and sit in the physical memory because of limited size.
So the TLB would also be implemented in the main memory only.
No,
So
no, TLB is not in main memory.
okay,
TLB
TLB
is
is not in main memory.
TLB is a special hardware uh, circuit which is part of the processor.
Okay, so you can from the TLB you can just easily check the
Yeah,
tag by
yes, yes.
comparison.
So it's a typically single cycle access to TLB and first level cache. Uh, yeah, so now what has happened is that we had a page fault for virtual page number one. We brought it and put it in physical page location 13. And we'll also update TLB entry. So something from TLB has to go, and we are placing this 113 entry there also. Okay, the idea is that you have brought in this page into memory there because of locality. You are likely to see more accesses to the same page, and therefore you expect some hits to happen. So indeed, the next access is to page 1, and that's a TLB hit. The next access is to page 2, virtual page 2, which is absent here. So there is a TLB miss. It is also absent here, so there is a page fault also. Okay, so again, similar process has to be undergone, and virtual page number 2 has to be brought in, and so on.
Excuse me, sir.
Yeah.
Sir, when a page fault occurs, let's say in case of one, this 7193, when a page
Yeah.
fault occurred, there was some data stored in a disk. So when we update this to, well, when we map page virtual page number 1 to PPN 13, will
Hmm.
the data now gained be transferred to the program in the same cycle, or will it be transferred later? Like this, in this cycle, will the data be transferred or not?
Oh, yeah. So now here it's not just a cycle. There'll be thousands of cycles. You see, you're moving
Okay.
4 kilobytes from disk to memory. All right.
Okay. Acha.
So
Yes,
essentially,
yes.
a program which is running, it encounters page fault, then the control passes on to operating system, and operating system will initiate the transfer from disk, which will take quite some time. And the meanwhile, operating system will start executing another process or another thread. Okay, because it cannot make the first program or first process wait for those thousands of cycles. So there is a switch made to OS for a few cycles. OS executes few instructions to initiate these transfers, and OS brings in another thread into activity and continues. So
So
when will the chance for the first process come again? It depends upon operating system policies. So eventually, at some point, uh, this first process where page fault occurred will be resumed and continue from where it left.
okay, so when this completes, like when we finish mapping it, then it will continue,
Yeah, yeah,
like based on the OS
yeah.
policies. Okay, thank you.
So between these two,
Yeah, I'm
between
hearing something, but not loud enough.
sir, between the two ones for corresponding to miss and hit,
Yeah.
uh, there would be a lot of other processes, right?
Uh, okay. So we are focusing on memory accesses. it's possible that there may be many other instructions executing between these two ones. Okay, so of course for every instruction also there is a memory access. So I'm not actually showing that. So for the moment, assume that we are focusing on some load store instruction, and program is running in program itself is located in physical memory. So um, we are not showing those instruction accesses. Okay, so now as you have page fault for physical virtual page number 2, you again bring it from disk and put it in physical page 14, make an entry for that in TLB and so on. Okay, so a variation of this example now with TLB organized as a two-way set associative structure, which means that we have two sets here. They were just 4 entries, like this. You have 4 entries in TLB. These 4 entries are divided into 2 sets now, and we need to look up for a VPN in one of the sets. Okay, you could say that the even one will be in this set, odd one will be in that set. Okay, so we look at the same address stream, same sequence of virtual addresses and corresponding VPNs. So we look up VPN 0 not present, so TLB miss. We would have actually looked at in this part only, where we are keeping information about even numbers, even virtual page numbers.
So in this case, we have a multiplexer ahead of accessing the
Right,
VPN,
right.
right? To check whether it is a even or not. Okay, sir.
So in fact, there'll be a multiplexer here also. The tag could match any of these, and therefore the data coming out of these locations has to be multiplexed. Okay. Here there is a multiplexing, one level of multiplexing within this, one within this, and then the result of 2 are multiplexed. So TLB miss, page fault no, and this entry is copied from page table for virtual page number 0, physical page number 5. Okay, the next is 7. We look up here, it's a hit. Then we look up 3, that's a miss. Okay, in the TLB it is a miss, but in page table it's a hit. Okay, so we put that entry here. It results in another hit, and then we are looking up 1, which is a miss, and also there is a page fault. So we bring it from disk and make an entry here. Yeah, question?
Sir, in this case, let's say we have some, we encountered that at 1, the disk, there was page fault at 1. So I have to replace 1 like in the TLB, right? But in this case, the odd part is already filled, like already full. It's all the columns are filled. But in the even part, there are rows which have 0, like V0. So will I do this, like, will I put this in the even part? Because that will be more exhaustive.
So you're looking for more flexibility. Then you have fully associative structure, which is more expensive. Okay, this requires only 2 comparators. Okay, the other one requires 4 comparators.
Okay.
So and in a similar way, you continue. For 1, they'll be hit next time, and next access is for 2, which is a miss in the TLB, and also there is a page fault here. So bring in that page from disk, put it in physical page number 14, and create an entry in the even part here. Okay. Okay, so that was the illustration of how things work with TLB and page table. Let me now move on to the next topic, which deals with the input-output subsystem. So we have talked of processor, we have talked about memory, and what remains is the input-output. So input-output, as the name implies, deals with flow of information into the processor or out of the processor, into the computer or out of the computer. So this is facilitated by a variety of devices which serve different roles. This picture shows some assortment of such input-output devices. Uh, their roles are different in the sense that they can be used to communicate with humans or other computers or the physical systems or environment. Okay. They could also be simply used for storing. It's not for communicating with human or outside world. These devices could also be used for storage. There could also be variation in terms of the direction of data flow, whether it is input or output. And there could be variation in terms of speed. So some are very slow, some are extremely fast. And the type of information. So you could be inputting, outputting text, you could be inputting, outputting sound or images or video or what have you. Okay. So devices which communicate with humans are essentially, keyboard, mouse, etc. So I'll have examples maybe in the next slide. So communicating with human is through devices like keyboard, mouse, joystick, which you have typically in games, tablet, where you can write or draw. You have touch screens. You have input specified through gestures. Okay, so variety of means are there. Uh, the humans also deal with documents. So you could produce a printed output, okay, through printers or drawn plots using plotter. Printed input or pictures can go through scanners. So that's these are inputs for documents and these are outputs for documents. Sound, input through microphones, output through speakers. Graphic display for any pictorial output. Some of these are very slow, as I mentioned. For example, keyboards would be catering to the slow speed at which you can type. So just maybe a few tens or hundreds of bytes per second. Okay, so data rate is very small. Uh, Scanners, printers, typically their speeds are defined in terms of ppm or pages per minute. So 8 pages per minute or 16 pages per minute. And what is there on page is specified in terms of dots per inch. So suppose you're scanning a picture, what is the density of the pixels? 300 dots per inch, 600 dots per inch, 1200, and so on. So based on how many pages per minute you are reading or printing, and what is the density of information on that, you get data rate in terms of some hundreds and thousands of kilobytes per second. Could see the difference here. Sound input output, they are medium speed in the sense that they are like tens or um, hundreds of kilobytes per second. Graphic displays require much higher data rate, okay, because depend upon again resolution of the display. So display will have some millions of pixels. So you specify it's so many megapixel display, and the display needs to be refreshed at certain rate. So it turns out a few uh, tens of megabytes to few thousands of megabytes per second. Communicating with machines. So this is input output happening between multiple computers. So a network, wired network or a wireless network, and there are different standards of these networks, different characteristics, different speeds, different range, and so on. Modems are the devices. Modem stand for modulator, demodulator, short for that. So devices which connect computers to analog communication channels like telephone lines. Uh, these also carry data at fairly high speed. Some could be thousands of megabytes per second. Um, okay, modems are somewhat slower. Communication with physical system or physical environment, you have sensors. For example, an embedded computer would be interacting with the environment, sensing various parameters like pressure, temperature, humidity, and so on, and providing control through switches, valves, solenoids, motor, and so on. The signals here could be simply on-off signals. You turn on something, turn off something, or analog signal, pulse train, whole variety could be there. Another category is the storage devices. So in terms of interface, these are treated like peripheral devices or IO devices, but these are essentially for storage. Uh, I mentioned some of this earlier while talking about memory. You have magnetic storage on disks and tapes, optical storage on CD-ROM, DVD, Blu-ray, and semiconductor storage in the form of flash, NOR flash, NAND flash. Uh, so, the kind of peripherals you have define the computing environment. So I'm showing a picture of, you could say, the first computer we had at IIT Delhi. So this was around 1970. It was a British. It's a machine from UK, and the only input and output it had was in terms of a paper tape reader and paper tape punch. Okay, so I don't know if you have seen this stuff. So it's like a strip of paper which is kept in the form of a roll. It could be rolled, and there are holes punched which form code of a character. Okay, so a sequence of character would be a sequence of pattern of holes, and here is a device which would produce such a tape. So the input you give to the computer would be punched on the tape through this typewriter-like device. That is read by the processor, computation done. The result comes back again in the form of a punch tape, and the same device could read and type the results for you. So not only data, the program, first of all, the program has to be punched. Okay, and that program is read, executed. For program execution, there will be data fed to it. Okay. Not only that, even the operating system has to be fed in the form of a program punched on tape. So it's fairly primitive, and compared to the current programming environment, this This is something which is shared among all the users of the institute. Okay, so it runs in what is called a batch mode. So uh, all the tapes, all the programs are fed one by one and executed one by one. So one program is fed, executed, results out, and then the next one is fed, executed. So it goes in a queue, and typically you would have to wait for a day for your result. So imagine that how careful you have to be with the program you submit. Okay, you miss out a comma, and only next day you know that this was the problem and you have to fix it. So that makes the programmers very careful. You'll spend hours making sure that what you're feeding in is good enough so that you don't waste a day for small tiny silly mistakes. Okay, what do you do if there is an error? Okay, how do you correct it? So you literally do cut and paste. Okay, you physically cut the tape and patch a correction with the sellotape and feed it again. Or if there are lots of mistakes, you retype it. Okay, you know, you can imagine the luxury we have in terms of programming environment compared to this. This is where our generations learned. Okay, things improved here in the sense that a line printer got attached. So it's a huge printer which could print one line at a time, and the results actually could got printed. So even the program could got listed here, and the result could be printed here. The programs and operating system could be stored on magnetic tape for subsequent usage. Then things which were added were punched card readers and disk drive. So punch cards are again, they are thick paper on which one card carries one line of your program. Okay. The advantage here is that if you want to make correction in one line, you remove that card and insert another card. So there is no cut and paste involved here. Okay. So in general, you can view the block diagram of a computer system in terms of these three parts. I think I've shown this diagram in earlier lectures also. So on one hand, you have processor, you have memory, and you have input-output devices. More realistic block diagram is something like this. That you have processor, you have cache, there could be multiple levels here, you have main memory, and you have various I/O devices connected through I/O controller. So, and there is some form of interconnection between these. We'll discuss this in detail later. There are many possibilities here, and we'll look at that. So let me give an example of a very small system which typically students use in our lab. Of course, if you go through a logic design lab in a physical manner, you will probably use this FPGA board. Basis 3 is the name of that board. If you were doing your COL 216 exercise on this, so in this RTX 7 FPGA, what you are seeing here, you will implement your processor, and it will have these very primitive input outputs in the form of a display, numeric display, these LED displays, and some switches which can be turned on or off. Okay, and these are push button. So it's a in terms of input output, it's a very simple system, and I'm bringing it in discussion just to elaborate on how a processor sitting here would be performing input output with these things.
Sir, are these switches physical switches or transistor switches?
These are physical switches.
So
So
like,
you
what
can
is the use?
physically turn them on or off. These are slide switches. That means you slide in zero position or one position. And the one you're seeing, which are labeled as buttons, these are press button. You press, it is on. You release, it is off.
No, I mean, what is the use of these slide switches?
Uh,
Why do we need it?
these are to provide 1-0 inputs.
Oh, okay. Like
So
the
these are the
instruction.
inputs. No, instruction, not instruction. So imagine that there is, you have using VHDL, you have designed and synthesized a processor. So that design would be implemented here in this FPGA. Okay,
Oh, okay.
and that processor could be connected to these switches and displays as input output. Okay, so that processor, we'll discuss how that processor could read ones and zeros from these switches. So there are 16 switches. You can get a 16-bit binary input, binary number.
So like for each entity, we have a different FPGA kind. Each component. Is it?
No. So suppose you design a process, you design ARM processor, some instruction set you implement. Okay, uh, that implementation would be within this. So this big block you see in the middle is a configurable piece of logic where you can create any design. So suppose you create a processor and memory here. Okay, then what I'm discussing is that how that processor can read the binary number presented by these 16 switches,
Okay, okay, got it.
and how that processor can display a 4-digit number over these. Uh, these are called 7-segment displays because, if you see carefully, there are 7 segments, 3 horizontal and 4 vertical segment, and you can display numeric values here. So you can display a 4-digit number here, and these are individual LEDs which can be turned on or off. So there are 16 of these. So you can display a 16-bit binary number here. You can display a 4-digit hexadecimal or decimal number here. You can read or you can input a 16-bit binary number from these switches, and also you can input a 4-bit binary number from these push buttons. So these are some primitive input outputs, uh, simple to understand, and as we go along, we'll see how we can work with these inputs outputs. Okay. So imagine that what is there in this big gray box is a processor, memory, and some other logic which will connect the processor and memory to these switches and displays. Okay. So what we are trying to see is that what is that logic? How do we connect processor and memory to these things? And from program point of view, what program has to run in that processor uh, to be able to do this read and write? Okay, input or output. Okay, so uh, these are the things which are there on the board, and a few things can be attached to it. For example, a keyboard can be attached like this. So a simple 16 button keyboard, which basically is uh, you can enter hexadecimal digits, so 0 to 9 and A B C D E F. Okay, and you can see these pins projecting here, and this plugs into some place in that board, so it becomes another input device. Okay. So now let's understand this 4-digit display a little better. So each of these segments in this display is basically an LED from circuit point of view, right? And so you have LED is like a diode. There is an anode and a cathode. When current flows through this, it lights up. If current doesn't flow, it doesn't light up. Okay. So cathodes are connected to these lines, CA, CB, CC, and so on. Anodes are connected to the wires which are above it. Okay. So now we don't need to get into circuit details too much, but essentially what you should notice here is that uh, for all these 7 segments, okay, so think of 7 LEDs sitting here, and their anodes are all tied up together connected to this. Okay, but their cathodes are separate. So 7 A, B, C, D, E, F, G, and DP. DP is for decimal point. So that's the 8th cathode. Okay, 8th LED, and so eight cathodes are connected to these 8 lines, and all anodes are common connected to this line. Similarly, for this group of 8 LEDs, the cathodes are connected to same 8 lines at the bottom, and all anodes are connected to this line. Okay, so how do you light up one particular segment? Is that you give a 1 at the corresponding anode input and give a 0 at the corresponding cathode input. So there would be some current flowing like that. Uh, so here is a more clearer illustration of how the circuit is. Yeah, question?
In the previous slide, those CA, CB, CC, CD
Hmm.
till DP, are these for just one part? Like there are 4 parts, right? So is this for
Yeah. So
just one part or
no, same group of 8 wires is connected to 8 cathodes of this, 8 cathodes of this, 8 cathodes of this, and so on.
So how will we distinguish, like if I want to light up only one part of the rightmost, this eight,
Yeah.
whatever it is,
So what is done
so it
is
will light
that
up all of them.
yeah. So what is done is that let us say you want to show 7. Okay, that means this top horizontal LED and the 2 vertical LEDs on the right. Okay, these 3 you want to light up. So you will and we are talking of this particular digit, second from left. So you give a 1 here, give 0 to other 3. So at a time you give 1 to one of these 4 and keep others at 0. And in the at the cathode level, so you give 0 to the cathode corresponding to these 3 LEDs. Okay, so out of 8, 3 are given 0, others are given 1. So those 3 LEDs will light up in 1 digit. Okay, and you need to do it in sequence. So you uh, display this digit, then display this digit, and then this, and do it at a rapid speed so that by persistence of vision you will see all 4 getting displayed. Okay, so the circuit is like this, that each digit is in this manner. There's a common anode which is feeding all the 8 of these, and their individual cathodes which are coming from the CACB and so on. So you need to display 1 digit at a time. Digit. So this is the horizontal axis, the time axis. You give uh, these signals. I'm sorry. I think I mentioned that you give a 1 here, but actually because of this transistor, the logic has to be different. So if you give a 0 here, then this transistor is turned on. Okay, so you give a 0 to one of them and 1 to the remaining ones. So you get waveform like this. AN0 is made 0 in this interval, then AN1 is made 0 in this interval, and so on. So essentially you are scanning these. Uh, the intention is to display digit 0 here, digit 0, digit 1 here, then digit 2, then digit 3. And from here to here is the period which repeats. Okay, so that's the refresh period, which has to be a couple of milliseconds, right? So when you have activated AN0, then you give on the cathode, you give a pattern which makes digit 0 displayed. Then in the next interval, you give the pattern on cathode which corresponds to digit 1 and so on. So the circuit would be something like this, that you have 4 digits to be displayed, each represented by 4 bits, and this multiplexer selects one to be displayed at a time. Okay, so one of these is selected depending upon a counter which is running. So this counter is going 0, 1, 2, 3, 0, 1, 2, 3, and so on. It selects one of these uh, corresponding to the current count. These 4 bits representing that digit are mapped to a 7-bit pattern which is applied to the cathode. And the anodes are driven by a decoder whose input is the counter. So this decoder is such that one output is 0 at a time, other 3 outputs are 1, and it helps in getting the digits displayed one by one. And if you run it fast enough, you see all of them getting displayed concurrently.
Sir, when let's say one of them displayed,
Yeah.
and let's say it is very fast enough so that I have to see them concurrently. So when
Yeah.
the second one glows, wouldn't the first one like switch off because
Yes,
the
yes.
signals have
So
changed?
at a
How
time,
I will
actually,
it
only
become
at a time only one is glowing. At a time only one is glowing, but your eyes will there is a persistence of vision. So
okay?
if you see something for a few milliseconds and it goes, your eye will perceive it for a longer period.
Okay, sir.
So many displays work like this. Even the video display, the the one probably you're watching now, uh, has it goes through a refresh. So if something is repeated, is refreshed at a speed of some 16 times per second or so, it becomes persistent. Your eye is not able to distinguish between uh, one image going off and other one coming. So you'll see a superimposition of all this.
So like at this moment, are all the pixels being lit up concurrently? They are being done so in like sequence.
Yeah, they are happening in sequence. Okay, so in
Okay.
fact, uh, it it would be so the refresh, if you see at pixel level, has to be extremely fast. Okay, so suppose your display is running is getting refreshed at 25 frames per second, which corresponds to say 40 milliseconds. Okay, so in 40 millisecond period, you are displaying thousands of pixels, although you're displaying only one at a time, but you see the effect as that all of them are being displayed concurrently. Okay, so
Okay.
in fact, even the display provides some persistence. The displays themselves have some persistence, and your eye does the rest. Uh, Now let's look at this 4 by 4 keyboard. So there are 16 keys arranged in 4 rows and 4 columns. So one way would be to look at each key as a switch, and you can simply read the status of those switches as a 16-bit pattern. It's okay for 16 keyboard, you can do it, but imagine the full alphabetic keyboard which you have. If you look at your keyboard where you are watching this, you would have you have 26 for letters and 10 for digits and so many special keys. So you would have uh, more than 50 keys, or some keyboards have even something like 100 keys. All right. So you can't have uh, so many 100 wires running from your keyboard to the processor. What is done is that you scan these keys and pass on only the code to the processor. So I'm showing the scanning arrangement here, that the keys are arranged in the form of a matrix. Okay, you have rows and columns. There is a counter, so some bits of the counter drive the row, and some some bits of the column specify some bits of counter specify the column number. Okay, so you in this particular design, what I'm showing is that one row of key matrix is sensed at any time, and these 4 bits will indicate if any key in that row is pressed or not. Okay, so that could be that pattern could be encoded into, let's say, a 2-bit code, which indicates which of, if at all, a key is pressed, which key is pressed. Okay, so looking at what row and what column the key which is pressed is located, you can get a 4-bit code of the key. And this idea holds for larger keyboards also. So the keys can be encoded uh, into a much smaller code, and only those many bits need to be input by the processor. So going back to our block diagram, we are now talking of a processor, main memory, interconnection, and only 2 devices, one 7-segment display controller and one 4x4 keyboard controller. So these are the little circuits. These controllers are basically this. Okay, so the processor is supplying only the digits which have to be displayed, and this decoding and scanning, all that is happening in a special circuit which is uh, placed close to the display. Okay, so we call this, you can call this as the display controller. Similarly, this circuit is the keyboard controller. Uh, it is also possible to eliminate, in this example, suppose we eliminate these controllers and we give low level control to the software. That means instead of having this hardware and this hardware, we simply connect we simply allow processor to control these inputs and outputs. Okay, so processor interacts at this level, and the job which is being done here by hardware could be done by software. Similarly, uh, the processor simply looks at the rows and columns and not the encoded value, and the scanning happens within the software. So we'll look at that possibility. Before we do that, let's understand how you see input output from programmer's point of view. So as you simulated input output, you saw the use of SWI instruction. So SWI instruction is essentially a call to some system action, system activity, including input output. So what happens that when you invoke SWI instruction, the control passes to the system or the operating system, which will actually perform input output. So the user is actually uh, it doesn't have to face the burden of doing it, knowing the details of input output. Okay, so there are standard ways of interacting with various IO devices, and that is captured within the operating system. So user could simply invoke or call those routines. But what OS will have to do is uh, perform the actual input output. And it could be done using special input output instructions. These instructions will specify which IO device we are talking of, uh, or which register or memory location is to be used for performing transfer. Okay, whether you need to transfer data from register or memory location to the device or device to register or memory locations. Okay. So such an arrangement is called dedicated IO. So you have to have special input output instruction. The other approach is to have memory mapped IO, which is in fact more common in larger system. This may happen in typically smaller system. So you treat the devices as memory locations. Okay, and you don't need special instruction. You simply use LDR STR instruction. So if you want to read data from a peripheral device, you do LDR. And when you want to write data to a peripheral device, you want to send something out, use STR instruction. Okay, so STR, LDR instruction, which are designed to work with memory, work with IO because now you are mapping IO devices to the memory. So in the first approach, you have separate IO address space. And in the second approach, you have memory mapped IO, where part of the memory address space is reserved for IO. And you use, if you do load store with those addresses, you don't read write with memory, you perform input output with the IO devices. And memory is supposed to ignore those addresses. In the other approach where you have special IO instruction, you have separate IO space. Okay, so IO address 0 would differ from memory address 0. IO address 1 differs from memory address 1. So they are separate IO addresses, separate memory addresses. Of course, the IO address space has to be much smaller. So memory address space is in megabytes and gigabytes. IO space could be in few hundreds or few thousands. So as the processor decodes instruction, so if it is IO instruction, it will send a different control signal to IO devices, and if it is LDR STR, it will send control signals to memory for reading or writing. Okay. So each IO device or device controller, if there is one, is viewed as a set of registers or ports by CPU. So CPU can use these registers to write commands and parameters, read status of IO transfer, or perform read write of data. Okay, so what we mean by assigning addresses to IO devices is that IO devices are viewed as collection of registers or ports by CPU, and those are assigned some address. So suppose address 100 is the command register for a device, and address 101 is the data register for a device. So the processor can write into those addresses, and thereby it will write command or data to those. So it is these registers which are addressable as memory mapped IO or dedicated IO, as we have just discussed. So as an example, suppose you have memory addresses going from hexadecimal 0000 to FFFF. Okay. Then you could say that, all right, from address FF00 onwards, I am reserving for input output. Okay, and that becomes your address space for IO devices. So I've expanded that here in this middle part. Uh, so some range of addresses assigned to each device. Let us say I have 16 devices, device 0 to device 15, and I assign 15 addresses to each of these. So FF00 to FF0F is device 0. FF10 to FF1F is device 1, and so on. Okay, so uh, now each device is assigned a range of addresses, and in that range, I'll basically have, so it's a further detail shown for this for device 1, that you have 4 registers which are required for the device, and it takes up. So if it is, let us say first one is FF10, next one would be FF14, FF1C, and so on. So these 4 registers are there for device which are assigned address in this range. So with the device controller, you need a circuit which will identify the address, decode the address. So for example, for this arrangement, uh, what you can see is that if the top 8 lines of the addresses are 1, then the address corresponds to input output. Okay, so address bit 8 to 15, if all are 1, then I have a 1 here, and that will indicate the addresses for input output. If it is 0, then indicates that the address is meant for memory. Okay, and the lower bits of addresses.
What are address 15, 14 to 9? What are these?
You see, I'm elaborating this example. So in this example, it has 16-bit address, right? 4 hex
Yes,
digits.
sir. Yes.
And the addresses which are FF00 onwards are for input output.
Oh, okay, okay, fine.
Okay, so therefore, the top 8 bits of address lines, that is address 8 to address 15,
Oh, yeah, yeah.
if all these are 1, then I understand that it's an input output address. If not, then it's a memory address. And address bit number 4 to 7 are telling me which device it is. So you could see that the third hex digits is indicating the device number. Okay, so I decode these 4 bits, ADR4 to ADR7, and this decoder will tell me which device needs to be selected.
Sir,
Yeah.
isn't there a fundamental difference, fundamental problem about viewing input-output devices as registers, as memory? Because the input or output would generally be in the form of pulses, right? Transient pulses, and there would be uh, uh, a gap in between where the signal would be just zero. So when we view it as registers, we are assuming that once we assign some value, then it would retain that value.
Hmm.
But in reality, it would
Yeah,
just get.
we can, if the value is transitory, we could actually in the hardware make arrangement that the value gets latched into a register. Of course, the timing issue will still remain, that you would need to know when the value is available. It may not be always available, so you need to actually sample it at the right time. So we'll come to those details shortly. Okay, so now we're talking of these signals running between processor and memory, address, data flowing both ways, and some control signals indicating read, whether it is read or write operation. So these signals are connected to memory, and they could also be connected to the IO devices. So this is where a bus comes into picture, that you have a bundle of these lines or these wires going to processor, memory, and various IO devices. Uh, so these IO device registers or ports would connect to the bus like this, that you have output ports, so which will take care of uh, storing the data coming on the bus into these registers. So these ports are like registers. At the right time, the data which is output by CPU on the bus is stored into these. And similarly, data coming from outside world is stored in these registers and read by CPU. So here is the logic which we'll be looking at: the address coming on the bus, uh, whether it's a read operation or write operation. So it will trigger this register when the address corresponds to this register and it is a write cycle. Okay. Similarly, this logic will enable this output of this to get into the bus if the address corresponds to this port or this register and it's a read operation or input operation. Okay, now let's bring in these small devices into picture and look at various things in context of these devices. So we can uh, communicate with the display by outputting 4 digits. Okay, so imagine that you have 4 registers in the display controller where processor can write these 4 digits and the display controller will take care of the rest. Okay, so the job of processor is to perform 4 writes at these addresses and write these digits. Okay, or since we are talking of 4 bits of each, in fact it could be, instead of 4 registers, we could think of it as a single register also. All we need to output is 16 bits. But just for conceptual clarity, let's imagine that you have 4 4-bit registers, which are like 4 ports, 4 addresses assigned to these, where processor can write 1 digit at a time. For keyboard, we have 2 input ports. Okay. On one port, we get a single bit information whether key has been pressed or not. Okay, and on the other port, we get a 4-bit code of the key. Okay, if key is pressed, then we look at this one, next one, and read a 4-bit number which corresponds to the 4-bit key. On the other hand, if we didn't have that controller hardware and we want to control everything by software, so it's a raw control or low level control, then for display we can arrange the 2 ports as follows. In one port we write 4-bit anode pattern, and in the other port we write 7-bit cathode pattern. Okay, and since we can do this for 1 digit, we need to, at suitable intervals, we need to keep writing for other digits also. So at one point of time, we write this for 1 digit. Then after, let's say we are refreshing, suppose at the rate of 40 milliseconds. After 40 milliseconds, we refresh the whole thing. So that means each digit gets 10 milliseconds. So at some time t, we write these 2 values for 1 digit, After 10 milliseconds, we write it for next digit and so on. So every 10 milliseconds, we need to change. Uh, Here in the keyboard, um, we are not getting encoded information. So we output row pattern. So which will select one of the rows of the keyboard, and we'll input the column pattern. So we'll read a 4-bit pattern indicating if a key is pressed in that or not. Okay, so one output port, one input port. And since we don't know when the key is going to be pressed, we need to keep keep doing this repeatedly at certain rate. All right. So that is the arrangement we have to make. Uh, I'll stop at this point, and we'll see further how we carry out this input output. Any question before we close?
Sir, in keyboard, why do we need repeated scan? Why can't we just store the result in some register?
Yeah. So you see, let's go back to these two pictures. Uh, you have two choices. Okay, one is to put these two hardware controllers in place. Okay, other is not to have these and then do what this hardware is doing in software. Okay, so the difference is as follows, that if you have this hardware, then you simply need to output 4 digits, whatever you want to display, and this logic will keep taking its counter, keep on refreshing and keep on doing that. So when you want to change the number, you change, but between one change and the next change, you don't have to do anything. On the other hand, if you don't have this, okay, simply you are interfacing with the display at this level. Okay, you are directly telling the pattern which goes to cathode and what goes to the anode, and then the processor has to intervene at a much faster rate. Okay, so at every 10 milliseconds, it has to output something.
Sir, could you explain this in case of keyboard?
Yeah, in case of keyboard, if you have this hardware, then this counter is running, encoding is happening. When a key is pressed, you get a 1 on this line, and you get a 4-bit code on these two lines plus these two lines put together. Okay, the processor has to only look at this key repeatedly, and when this key is 1, it reads this 4-bit code. If you don't have this decoder, encoder, and this counter, then it has to keep changing the row number. It gives a pattern which activates first row, looks at the columns. Then it activates second row, looks at this column output. So it has to keep doing this at a much faster rate. Okay.
Okay.
Yeah.
Thank you.
So in the first case, when a key has been pressed, okay, this information would remain available from that time onwards till the processor says that yes, I have seen the key. But in this case, you know, in the other case, when this hardware is not there, the processor has to scan this key matrix at rate fast enough so that when key is pressed and released, you shouldn't lose it out.
Sir.
Yeah.
So I had a doubt regarding the assignments. Like in VHDL, can we use case statements which are non-exhaustive?
Uh, in in a clocked process, yes, you can. It might still give you a warning.
Sir, there is an option for null. We say when others just do null, but do nothing.
Yeah. So it is okay in a clock process because you're defining sequential synchronous circuit.
Yeah.
But if you're using a process to define a combinational circuit, then make sure that you have the others clause. Okay. So wherever you're defining a combinational circuit, make it exhaustive. Whether you are doing selected signal assignment, conditional signal assignment, or case statement within a process, or if statement within a process, make it exhaustive. Otherwise, a latch will be created, and that will be a headache when you try to debug.
Okay, sir.
Yeah.
Sir, and another thing was that regarding the multi-cycle stage,
Yeah.
can we like embed the controller within the glue logic only, like have one FSM which contains the glue logic and the controller also?
Yeah. So my recommendation is that this the process which is defining FSM, use that process to clock the register which you have in your glue logic. Okay, but not but separate out the combinational circuit.
Sir, actually, the problem with that would be be that like you have multiple control signals, and for a particular state, you only require a small subset of those uh,
Yeah. So
control signals.
one easy thing is that you have one process which is clock triggered to define state transitions and
Yeah.
clocking of the registers. You have another process which is used to define the control signal and other and rest of the glue logic. Uh, make this process combinational. Okay, this will also have a big case statement which is controlled by the state. Okay, so in different state, whichever control signal you want to activate, you show that. Before the case statement, you make default assignments. Okay, so uh, if all the control outputs, if they or other even data outputs which are coming out of this, if they have a default statement, then you don't have a problem. It will remain a combinational circuit. But if you don't have default assignment and you are making assignment only under certain state, uh, then it will imply storage and latch.
Sir, so it's fine if we make the controller uh, and the glue logic within the same file, just that we have to
Yep.
make it in different
Put
processes.
in the same architecture. Put in the same
Right,
architecture,
right. Okay.
but keep two processes separate.
Okay, sir.
Yeah.
Thank you, sir.
Okay. We'll close now. Thank you.